Okay, I'm going to start a new show. It's called TempleOS 5-Minute Random Code Walkthrough. And I'm your host, Terry Davis. And here's the deal. There are 130,000 lines of code. And that includes both the demos, applications, and the main operating system. What we're going to do is use a random number generator to pick one of the 30,000, and this is the same generator that's from God, that causes God to talk. So in other words, God's going to pick a random spot, and we're going to talk about it. So here I go. Alt B. This was for finding bad code, using God to find it. Anyway, so here we go. Alt B. Where are we? We are in the compiler backend floating point. Oh boy, this is some nasty code. Okay, so let's see where we are. Intermediate code floating point. Intermediate code floating point. Compare and branch. Okay, so let's just start with whatever routine. So what this routine does is it's called in the last passes, and it converts so if we say let's see if we can generate that. Compare and branch. If f less than or equal to so we just want to execute. Okay, so we do trace on, and branch grader. Okay, so this is doing a floating. Let's see if we this is floating point. The reason I know that we just hit that code is because on the last compiler pass, it does 0, 1, 2. Anyway, on 7, 8, and 9, ICF compare. So in order to call that code, we have to have a floating point branch greater equal. That'll call the floating point or the other one. So what this routine does is it converts this branch greater equal to machine code. Okay, so this takes an argument. How many arguments does it take? We have I think we have one argument. No, we have two arguments. Greater equal. Okay, branch greater. There's two arguments, left and right side. There's a comparison operator. Okay. So what are the two arguments in this case? Oh, in this case it's comparing to 1. 3FF is the binary representation of 1.0. So we're comparing 1.0 to a value off the base pointer. This is a variable. Now it couldn't use a register variable. That's because with floating point operations you can't use CPU registers. So this loads fload. Oh, we're running out of time. Okay, so fload compare. This is the floating point stack. And then it frees it, and then it jumps based on the. We got this compare IP set the CPU flags. Okay, so long story short, there's what this routine does is if the last operation was a float, then we try and use the floating point stack to like if you said compare to 1 plus I, it would try and use the floating point stack as a register variable. Okay, so let's look at where it codes the instructions. So here's where it codes the loop. If you have a 3-part conditional, that's where we get this. I'm going too fast. I don't have enough time. Push compare. So here's where it's explaining what instruction. So this is the machine code, and it checks to see if it can do a short jump or a long jump. When we're compiling and making machine code, it does 7, 8, and 9. It does 3 or more passes, and the secret is each pass it can only get more condensed. Otherwise, and then the last pass, things are not supposed to shift around. So what this is doing is checking. It's checking right here, right here, if it can use a short jump. And if it can use a short jump, then it codes a short jump. And if something changes, then we let's see, for relative, some code you can skip on the last 3 passes. You just go once. But this code, it has to set the I think we set the not finished flag. Where is that? For RIP relative, you always have to redo the instruction. I think we want the final flag. Where is it setting the final flag? Oh well. Anyway, let's. For RIP relative, you have to redo it each time. So there's where the compare the branch is. Then this is where the floating point stuff goes. Oh well, and it has to handle. It has to handle a situation like 0.5 less than. It has to handle a situation like that, my special 3-part conditionals. And that's where this push compare, what it does is it's 2 operations. It's 0.5 less than F and F less or equal to 1.0. So it's 2 operations is how it codes it. And what it does is it always pushes the shared middle term. It pushes it, and so that's where this push compare. Anyway, it does short circuit logic. So what are we doing? So somewhere in here, one of the things we pass into this routine is the unsigned. This is unsigned, and this is the opposite. So if you have, this is kind of an interesting point. You have what's the opposite of less than, or do we want the opposite? There's, if you have left and right, you change like that. The opposite is greater equal. Well, let's see. Okay, so on on the last pass, I'm running way over time. So we want F compare. So it's passing in on this greater or equal 7383OF or 7686. So what that is 73 or 86. If we go to the opcodes 73, jump above or equal. The other one was 86 or 7. I don't remember. 76. Below or equal. Anyway, so above or equal. I think it's the. Oh well. So how about that?